Hey, hey,
Hello, Jenner.
how are you doing? Can you hear me?
Yep.
Okay.
Aha, there's a cool background now, Jenner.
Yeah, I bring you the tropical beaches of Indiana.
Humid, yes, very humid. Just like
Yeah,
a real tropical beach.
yeah.
We did get down to Lake Monroe, the beach at Lake Monroe a couple times this summer. That was nice.
Nice.
Not quite as nice as the one in your background, but
Yeah.
all right, let's go ahead and get started. So I'd like to start off with just some comments about things that we've talked about over the last week or so, and some general announcements. And then we'll pretty much pick up where we left off last time. Um, First, with respect to your GitHub repos, I'd really encourage you to get those going ASAP if you haven't already. And also, I'd appreciate it if, by later today, if you could add me and Jenner as collaborators to your GitHub repo. And there's a couple of reasons for this. One reason is that it's especially convenient for us to give you feedback by just putting the feedback straight into your files. Now, there's also this complication about whether you've chosen to make your GitHub repo public or private. You might not want the feedback in a repo if you've made it public. I'd recommend making it private, and then we can go ahead and put your feedback right there into some of your files. I mean, we'll also be giving you grades on Canvas as well, of course, but it's just sort of easier to do it on GitHub. So sort of the preference there is that you go ahead and make it private, but then add Jana and I as collaborators. It'd be great if you could do that like by today. That'll also help us if you've got questions about about your compiler. It's easy for us to just go ahead and clone your compiler onto our computers, run the code, reproduce whatever problem you're seeing, and then give you advice about it. So that makes for a very easy workflow for us. Okay, that's that. I think there's also maybe a little bit of questions or confusion about concrete syntax versus abstract syntax. and what your compiler has to do with these things. Okay, so I just want to say a few words about that. Right, the concrete syntax is the file like on disk that has the sequence of characters in it for the program. So like in the test directory of the public support code, there's a bunch of .rkt files, racket files like R1, you know, _0 or _1, 2, 3, and so on. Those are all example test programs. And in those files, you know, it's just text, okay? Now text is okay for humans to type in using a text editor, but it's terrible for a compiler to use internally to decide how to compile from one, you know, from one pass to the next. So that's why we use abstract syntax trees. And thankfully, we're, you know, to make your lives easier, we're providing the functions that turn concrete syntax into abstract syntax. So those functions are in the utilities file, okay? And in fact, you don't even have to know about those functions if you're just using interp tests, sort of that function. Under the hood, interp tests, you know, reads those programs in from the files, turns them into, you know, abstract syntax trees with the using the structs that have been defined in utilities, and then that's what interp test feeds into your passes, okay, to the first pass in your sort of list of passes. Alternatively, you can, if you want to sort of go under the hood, you can go in and look at the various internal functions inside utilities. There's a function called read program. There's functions called parse program that are involved in going from the text to the abstract syntax. In particular, the parse program function goes from an S expression representation to the abstract syntax. Okay, but to make a long story short, you should really only have to deal with the abstract syntax trees in the code that you write. Okay. One other thing I'd like to say about that is that if you'll notice up at the top of the run tests file that's in the public support code, there was a comment about debug level, and if you uncomment that and set debug level to 1, you'll see sort of the intermediate result from every pass that runs in your compiler, okay? And then if you go ahead and do a poll and get the latest utilities and the latest run tests, you'll see I've added another commented line that concerns this Ast output syntax. And what you can do with that is, so right now the default is when I'm printing out the abstract syntax trees, the default right now is that it prints it out using concrete syntax. And that's nice in that it's a very concise format to look at. Okay, so if you're looking at a big program, it's sort of easier to understand what that program looks like. On the other hand, it does lose some information that sometimes is critical to understanding what's going wrong in your compiler. So I've just recently added, as of like yesterday, this ability to say instead, oh, please print out the abstract syntax tree as abstract syntax, showing me all the gory details, okay? And so if you uncomment that line out, if you comment that, you know, get rid of the commenting and let that line back into the run tests, you'll see your abstract syntax as abstract syntax, okay? So hopefully that's helpful for y'all. I think that's the main things I wanted to say. Any other questions about what we've talked about so far, issues that have come up as you've been diving into writing those compiler passes? Okay. Well then, without further ado, let's dive into to where we left off. I'm going to pull up, share my screen here. Oops, that was the wrong, or was it? Oh, there we go. Good. Okay, so hopefully you can see the diagram of all the passes. And so far we've talked about uniquify. That was taking us from R1 to R1 with all the variables having unique names. We talked about remove complex opera star. That one inserted a lot of temporary variables as let bindings, making sure that all the arguments to things like plus and subtract and negation, that all those arguments are simple expressions, just, or atomic expressions, just variables and numbers, okay? And then we talked about explicate control, which for R1 amounts to flattening those let bindings into just a sequence of assignment statements. And then your program ends with a return statement. Okay. And then what we have left to talk about is this, in some sense, this back half of the compiler, which will start with selecting instructions, assigning variables to their homes, patching instructions, and then finally printing the x86 abstract syntax into its concrete syntax as text. Okay, one other little thing to maybe mention is that, you know, so we're going to pick up here with our C0 program. Okay, so it's got assignment statements and return, still has lots of variables in it. When we do select instructions, we're going to be going into what I'll call Sudo X86. Okay, it's not real X86 yet. It's close though. What makes it pseudo is a couple things. One, it still has variables in it. Okay, so it doesn't quite match the exact grammar for X86. Okay, additionally it has grammars, it has variables, and it doesn't follow all the rules for X86 instructions. Okay, so for example, an X86 instruction, if it has 2 arguments, only one of those arguments can be a memory reference, not both of them. Okay, and so our Sudo X86 might break that rule. Okay, and so basically these next 2 passes, assign homes and patch instructions, are all about sort of getting good with x86 in terms of not breaking any of the rules. So assign homes gets rid of the variables, patch instructions changes instructions that maybe are accessing too many memory locations. All right, so with that, let's go ahead and dive in to select instructions. So fast forward here, past all the good stuff we talked about last time, on to select instructions. Okay, so the example I want to talk about, I'm just going to, for the most part, the translation here is going to just look at one statement at a time and then convert it into one or more instructions. So let's look at some example statements. You might have a statement like this: x equals plus 10 and 32. Okay. Again, I'm writing in the concrete syntax here, but this corresponds to an assign node in the abstract syntax tree. And then now we need to convert this into some x86 instructions. Okay, now let's think a little bit about this. I mean, maybe the first question is, ideally, we'd like to turn these statements into as few instructions as possible. So it'd be great if we could just turn it into like one instruction. And so maybe the first question is there an x86 instruction that we could turn this statement into? Actually, this is kind of funny. I just thought of I have one answer in mind, but I just thought of another one.
Uh,
Maybe a bit more
uh,
smart alecky of one.
I think no. We need at least two, but if it's in like return, we could have done it. Otherwise, I think
Yeah.
it's no.
So Aditya, what do you think we should compile this to?
Probably first initially we move 10 to X and then add 32 to X.
Right. Yeah. Yeah. So that's what I'd recommend for that kind of situation. I mean, you might think like, oh, well, maybe like if you implement the partial evaluator part of your assignment, then you'll just never see examples like this. But instead, you might see a slightly different example. Here, I'll put it over here. And then you'd have to take this approach. So let's say you had X equals plus Y and Z, right? Then in that scenario, you definitely need to use the same approach. You'd move maybe Y into X and then add Z into X. Okay, so the partial evaluation, and then imagine that Y and Z are coming from read. There's no way you're going to partially evaluate that. So you need to, do this instruction translation. Okay. Let's look at a slightly different example. What if we have something like this, plus 10x? Now, obviously, we could use the same approach that we did in these other two examples. We could do a move and then an add. But can we do better in this case?
Can't we just add 10 into X because it has to be already defined?
Yeah, that's right. That's right, Sam. Yeah.
But how can we like generalize this? Should we like manually go and check if it's like a int value or and then?
Well, it's not so much that it's the, okay, that's a great question or point. So it's not the fact that it's an integer.
Mm-hmm.
The 10's not the reason why we can do this. What is the special case here? What is the...
I mean, X is the reason, yeah.
Yeah, that's right. It's the fact that we've got the target is also one of the source. And in fact, let's say we had X equals, plus X, Y. Okay. So I've changed a couple things about it. Now I've got the X on the left-hand side, and instead of the 10, I've got Y over there, some variable. We can still do add Q, and this time it'll be add Q, whoopsie, Y to X. Okay. Right, so basically whenever you have the target is the same as one of the arguments to the add, then you can manage this single instruction version.
Okay.
And yeah, so this is a little bit of special casing, and the name of the game is to special case using the right sort of predicates in your compiler. Like, what are you testing for? In this case, we're testing for, like, is the target the same as one of the arguments? Okay, and then doing the nicer code generation for those cases. Now notice that if you just use this approach for everything, your compiler will work perfectly fine. You'll pass all the test cases, and Jenner will give you an A for the assignment. Okay. So this one, if you adding this sort of specialization down here is just for pride. Okay. And if you're a production compiler engineer, you would be worried about the execution time of your programs that you generate, and maybe your yearly bonus might depend on having those spec benchmarks running faster, and so you'd want to do stuff like this. Okay, and that's a real concern. So like indeed my version of the compiler does these special cases, just because you want to generate the best code possible.
Yeah, that makes a lot of sense. Thanks a lot.
Okay, let's look at a couple more scenarios here. What if you have an assignment statement like this? You've got a call to read. Okay. So the read, you don't have to like implement that in x86. We've got this file called runtime.c that we've given you, and it has a function called read_int inside of it. Okay, so you just need to call that function, and so you can just use a call queue instruction, and then read_int. Okay, to call that function. By the way, you need to make sure that you turn that runtime.c into a runtime.o using GCC, and then you need a link when you use GCC to compile your x86 code. You need to make sure to link in and include that runtime.o file. Okay. Okay, so when you call readInt, getting back to the x86 calling convention, the result of a function call is put into the RAX register. Okay, so at this moment of time, after the call has happened, and now we're back, we're done doing readInt, and now we're back executing our program, the RAX register has the result. Okay. But we don't want the result in RAX, do we? Where do we want the result?
X.
In the X variable. Should have maybe picked a different name. It sounds too much like RAX. So we need to do a move from RAX into the X variable. Oh, just a little typo in my notes. Missing a comma. All right. Okay, we've got one more kind of instruction I want to talk about, which is the return. Okay, you've got return and then some expression. Okay, and then we need to convert that into something. Okay. And the way I think about what needs to happen here is that the result of this expression E needs to go into RAX. Okay. And so we essentially need this to act like RAX, like as if we were doing an assignment statement like that. Okay. And then we need to translate that into some instruction. Let's call it inster. Okay. And then that's we need to lay down that instruction. And then after we're done putting the result into RAX, then we need to jump to, we need to go to the conclusion of the main function. And I'm going to recommend that you use a label called conclusion for that. And we're going to talk in a little bit later about what code are we going to stick underneath that conclusion label, okay? But it's basically, there's a bunch of things that every function has to do at the end to be a good citizen, okay? And we're going to put that under the conclusion label, okay? Right, so and then the question is, well, how do you get from this assignment down to the instruction? Well, it's going to be one of the cases we've already talked about, okay? So it might be that the expression E was a read, or it might be that the expression was an addition or whatever. And so one of these previous cases applies, except that instead of having a variable on the left-hand side, like X, now you have a register that you need to use in place of the X. So internally, my compiler literally creates sort of this fake instruction or fake statement. It's fake. It's sort of fake in that, like, normally C0 doesn't allow registers on the left-hand side, but my compiler sort of says, okay, whatever. I'm going to create this sort of fake assignment statement with an RAX on the left-hand side, and then compile that down to an instruction using, you know, just a recursive call to the select instructions, you know, function, and then I lay that down and then insert the jump. All right, so that's the last thing I wanted to say about selecting instructions. Any questions, concerns about selecting instructions? Well, maybe one thing, I'll remind you that in the back of the book, there's a table of x86 instructions and a very brief explanation of what they do. That's probably enough for you to sort of decide what instructions to use. And you don't really need other instructions. That being said, if you're really excited about x86, on the course webpage, there is a link to the full Intel manual that has the 1,000 some odd x86 instructions. Though that being said, I think our interpreter that we use for testing doesn't know about other instructions. Okay, so if you were to use other instructions, you'd have to maybe send Jenna a note saying, oh, we've used some weird instructions, and then if in that case, we can still run your compiler end to end and test the executable, but we won't be able to like give you, it'll be harder to give you partial credit for like your intermediate x86 program, your Sudo X86 programs that you're generating. Okay. Any other questions? All right, moving on. So the next thing we're going to talk about is assign homes. But before we do that, we need to talk a little bit about where we're going to be sticking these variables in memory, okay? So we need to talk a little bit more about the procedure call stack, and in particular, call frames, okay? So if you remember, earlier we talked about how we've got, you know, the memory of a memory space in your computer, and there's like the heap, part of your memory is dedicated to the heap, and then part of it is dedicated to the stack, okay? And we talked about how every time you call a function, there's some space on the stack that's dedicated to storing the local variables, the parameters, and the address and memory of where that function is. that's all stored in the frame. So you get these frames that keep getting pushed onto the stack, and it grows downwards as you're pushing frames on the stack, and then as you're completing function calls, you pop them back off the stack and go up. Right, so each one of these is a frame, okay? For a particular function call. So we're gonna zoom in now on what one of those frames looks like. Okay, so we're gonna zoom in. Maybe this frame here. Sort of zooming in now. Now, earlier I mentioned that there's two registers that we're going to use to sort of keep track of the current frame, okay? So there's RBP, and BP is for base pointer. So the B and the P there. And then there's RSP for stack pointer. SP. Okay. Now, the frame, we're going to talk about the frame in sort of 64-bit chunks. Okay, so this, each one of these boxes is a 64-bit chunk. And the very first block here is going to contain the return address. Okay, so that's going to be the address of the instruction that comes after the call queue. Okay, right, and the idea is that when this current function is over, we're going to jump back to whatever address is stored in that first slot. And this first slot, maybe the next thing I should say is that the RBP is always going to point to the second slot. Okay, so this second slot is going to be offset 0 of the RBP. So let me make this a little bit wider. Okay, so the return address, if we're gonna refer to that, we're gonna refer to everything in the frame relative to the base pointer. Okay, so this is just above the base pointer by 64 bits, which corresponds to 8 bytes. Okay, so these offsets are in terms of bytes, right? 8 times 8, 64. Okay, so 8 bytes. If you move up 8 bytes from the base pointer, you get to the return address. Okay, now the next thing we need to talk about is, well, what's in that, what's stored at the location of that the base pointer is pointing to? That's going to be the old base pointer, okay? The old RBP is going to be stored there, okay? Because we don't want to, like, whoever called us was using their base pointer, and we don't want to wipe out their base pointer. So we're going to stash the base pointer in that slot, and then we have to put it back at the end. Okay, and so that's when we talk about the prelude and the conclusion of a function, we're going to talk about putting the base pointer, the old base pointer, in that slot. Okay. Okay. Then now the rest of the frame is going to be for our internal use for all the variables in our program. Okay, so basically you're going to have lots of variables potentially. So let's just pretend that we've numbered them 1, 2, 3, you know, up to n. So variable, oops, I didn't mean variables, just one variable. So variable 1 will go into that, you know, third slot, variable 2 goes in the one after it, and on up, okay? And so that first variable is at -8 of the RBP, okay? Then the next one's at -16 off of the RBP, and so on. Okay. And that's, so the way you're going to talk about assigning homes to variables is you're going to say, okay, I've got variable X, that's my variable number one. I'm going to replace X in all my instructions with -8 RBP. Okay. Now I haven't yet talked about the stack pointer. Okay, the stack pointer is always going to point to the last variable. Okay, so the 0 offset of the stack pointer is always going to be pointing to the very last variable. There's an important reason for the stack pointer, okay? When you call another function like readInt, okay, readInt is going to look at the stack pointer to know where to start stashing its own stuff. Its return address, its base pointer, you know, or our base pointer, and then its variables. And so we need to make sure that we've moved the stack pointer to the very end of the data that we're using, so that when we call that other function like readInt, we don't want it to stomp on our part of the stack. We need to make sure that it sort of moves on to a different part of the stack. And this is really, it's the RSP that's really sort of giving you this sort of push pop behavior that we want with frames on the stack. Okay, it's not like the stack doesn't just magically push and pop frames. It's like you got to move the stack, the RSP, to get that behavior. Okay. So yeah, so if you get like mysterious behavior when you're executing your program and it happens every time after you call readInt or something, then maybe it's because you haven't put the RSP in the right spot. Okay. So you need to know how many variables are in your program, and you need to make sure to move the RSP down past all your variables. All right. So this was my spiel about what frames look like. All right, any questions about frames?
Do we have some kind of a debugger as a part of our tooling where we can see all these memory changes?
That's a great question. The answer depends on what computer you're using.
Mm-hmm.
And this is actually part of the benefit of that we're generating x86 code. So you can use sort of standard debuggers for x86. So you can use GDB if you're on a Linux machine. And if you're on a Mac, you can use LLDB. Okay.
Okay.
If you've never used those tools before, there's a bit of a learning curve. They're not exactly easy to use. I always forget how to use them in the year or so between teaching this class, and then I have to relearn how to use those tools. I will say this though, it is worth it to learn how to use these tools. Okay, both GDB and LLDB give you the ability to step one instruction at a time through an x86 program. You can print out the contents of registers, and you can see what's happening. You can print out the contents of memory, what's happening on the heap. You can really see everything. It does take, you know, a few hours probably to get up to speed with those tools, but definitely worth it. And so, you know, that might be something that you want to do soon in the next week or two. I mean, it's possible to sort of limp along without learning those, but and in some sense, by providing interpreters for all the intermediate stages of your compiler, we're trying to like catch errors as early as possible, because once you're dealing with x86, now you're stuck, you know, using GDB and LLDB, and that's sort of a certain level of pain in that. And so we're trying to prevent that, but it is bound to happen that you'll have something going wrong where it passes all the interpreters, but then dies at the level of x86. That happens. It happens to my version of the compiler. And sometimes you just have to, get out GDB and use it. Jenner has his hand up.
It also defeats the purpose of using NanoPass style compiler because if we were not doing NanoPass, then all we had would be end-to-end testing. But because of the NanoPass, we had this great technology that we can individually test single passes because everything's independent of each other.
Yeah. Yeah. So yeah, this is definitely one of the huge advantages of our NanoPass approach, is that we can minimize the amount of time that we spend in GDB or LLDB. But unfortunately, it still sometimes rears its ugly head. Okay. So great question. Oh yeah, and there are lots of tutorials out there on the web. And if you find ones that you particularly like, feel free to share those amongst yourselves, or even share them with me and Jenner, and I'd be happy to post those links. I forget whether I have anything linked to from our course webpage. If not, that's sort of a good thing to add. Yeah. Okay, any other questions? Okay, let's go on to talking about assign homes then. Okay, so let's kind of think about an example program like plus 52. Actually, no, let's do a slightly more complicated program. Negative 52, negative 10, maybe, something like that. So maybe that was our input program. And then maybe, the remove complex opera star, maybe that turned it into this program that has a couple temporary variables. Okay. Like so. And then that in explicate control will get flattened out into a program where we now know what our local variables are. That's T1 and T2. And then the actual program, has like a start label, and it says, okay, we're gonna do an assignment of negative 52 into T1, and T2 gets negative 10, and then return, plus T1 and T2, right? So there's explicate, and then we do instruction selection, and so we still have these local variables there, T1 and T2. But now, we've got, a bunch of instructions, right? So maybe like move Q52 into T1, and then neg Q of T1, and then maybe move Q of 10 into T2, and neg Q of T2, and then maybe add Q of T1 into T2, perhaps, and then maybe move Q of T2 into RAX, right? I'm not sure if this is exact. I'm kind of going off the top of my head here about how the, my compiler would do it. Yours doesn't have to do it exactly like that, but anyways, so it's going to look something like that. And so we've got these local variables hanging out, and we've got them being used in all of these instructions. And we need to, and the job of this pass is to get rid of those local variables and replace them with slots in the frame, in the procedure call frame. Okay, so perhaps the simplest thing to do is just say, okay, for every variable, we need to map it to a slot. Okay, so maybe T1 goes to -8 RBP, and then T2 goes to like -16 RBP. Okay, so you need to come up with a mapping, and that should be pretty easy to do. You can basically just iterate over your list of local variables and just keep giving them, just keep bumping up the offset number by, well, bumping down, I should say, by 8 bytes, starting with -8. Okay, so you create this mapping for all of your locals, and then you need to iterate through your program, applying that mapping to all the variables. Okay, so you could imagine, you could represent this mapping with an association list, kind of like the environment, that we've been using for other purposes. Like in Uniquify, we had a variable to variable mapping. Now what we're talking about is a variable to, RBP offset mapping. Okay. And then so then you want to iterate through your program, and then every time you see like T1, you want to replace that with, with what it's mapped to, so -8 RBP. When you see T2, you want to replace that with -16 RBP. Okay. So this pass should be pretty straightforward. And you can see why it's kind of handy that we have the list of local variables, stashed. Remember, that's stashed in the inside of our program AST node. There's that info field, and if you recall, in the explicate control pass, the book says, suggests that you put the locals information in that info field. Okay. And then it'll be there for you when you need to use it in this assign homes pass. Okay. Any questions about that? And actually, one quick question. Am I waiting long enough for questions? I know that it takes some time to process what I've said and to really digest it before you can even formulate questions. So if I'm rushing too fast, just maybe go ahead and in the chat client, you can feel free to say like too fast or too slow or whatnot. Is it okay? Thumbs up or so-so? Thumbs up. Cool. All right. All right, moving on. The next pass is patch instructions. Okay, so I'm going to continue with that same example that we just talked about. So we had this move queue of 10, oops, of 10 into, I guess, yeah, let's call it, I guess I flipped up in my mind which temporary went in which stack location. So bear with me. So I've got this one going into -16 RBP. We've got neg Q on -16 RBP. And then we've got a move Q here of -16 into -8. And then an add Q. Oh, actually, you know what? I'm sorry. The example that I'm doing here is the original example that I had in mind, and I flipped it up, actually. Yeah, actually, let's go ahead and I'm going to copy this and work on this one instead. This is what happens when you go off of your notes and go ad lib. Oops. Let's try that again. Oh, I'm forgetting how to, oh, it won't let me paste from one screen to the next. Okay, well, actually the only really important thing here is this add Q at the end. Okay, so let's look at what that add Q looks like. We have add Q of -8 RBP going into -16 RBP. Okay, so this is what, after we've done our home assignment, this used to be T1 and T2, but now they've been turned into stack locations. And now what we've got this problem that in x86, every instruction can have only one memory reference. And what we've got here is 2 references to memory. When you're going to the stack, that's a chunk you're going into memory. You're not just, whereas if it was just an intermediate like $10, that's not an issue, or referring to a register like RAX, that's not an issue, right? These are non-memory. Whereas when you're doing an offset into memory, like this, that's an issue. Okay, and we've got 2 of them here in the same instruction, and we're only allowed to have 1. Okay, so we need to somehow turn this add Q instruction into a different sequence of instructions where we only reference 1 memory location per instruction. Okay. And so the way I recommend doing this is, 1, we need to reserve a register that we're going to use for this sort of patching up purpose. Okay. And I'm going to suggest that we use the RAX register for that purpose. Okay. So what we can do in this example is, let me think for a second. I think what you'd want to do is move the target, so that's your RBP, the -16 into RAX. And then once it's there, you can do an add. Actually, no, I take it back. Let's do the argument, -8 into RAX. And then we can add Q RAX into -16 RBP. So we've expanded that one instruction into this sequence of 2 instructions where, you know, we used to have 2 memory references. Now we just have 1 memory reference in this move and then 1 memory reference in the add queue. And now the other argument is a register. So we're okay. Now, the downside of this approach is that later on when we do register allocation, we won't be able to use RAX for arbitrary variables anymore. We're gonna be just reserving RAX for this one purpose. And that means that sometimes since we have fewer registers to use, sometimes we'll have to, some variables won't get a register and will be put on the procedure call stack. So sometimes we'll generate slightly less efficient code than maybe what we could have done if we had sort of not reserved RAX, okay? Now, if you don't reserve RAX, how on earth do you deal with this problem that patch instructions is solving? Well, what you can do is you could iterate register allocation and instruction selection. And you could iterate that sort of over and over again, and trying to find sort of better ways of allocating variables to registers. And as you're iterating, sometimes you have to maybe insert some extra instructions like you've done here, but that's sort of an orthogonal issue to choosing what variables go in which registers. But that iterating approach is harder to debug, to tell you the truth. So for our sort of educational purposes, I think it's sort of easier for y'all to just go ahead and do this patch instructions. Okay. It's also, in terms of compile time, this is a fairly fast approach. All right, any questions about patch instructions? Okay, now we're on to our final pass, print x86. So the main part of this pass is pretty trivial. It's really just turning x86 abstract syntax, AST, into x86 text, right? You just have to generate some strings, and that's that. So that's pretty straightforward. You may need to look up some Racket standard library functions for doing things like appending strings together or splicing strings into other strings and whatnot. Okay, but that's pretty straightforward. So the main thing I want to talk to you about is this. The other thing you have to do in this pass is to generate the prelude and the conclusion. Okay, and so let's talk specifically about that. So your program, if this is your text file that you're generating for your x86 code, So you're going to have this start label, and then underneath that is going to be all the x86 code that actually came from the input program, okay, and that came out of, you know, all the previous passes and that you've now turned into a string, okay? So that's going to go where all the squiggly lines go, okay? I need to save some more space. Okay, so, and that's underneath the, and if you recall, that code that you're generating is going to finish with a move queue of something into RAX, right? Because this is what our return statement does. And then it's going to do a jump to conclusion. Okay. All right, so we're going to talk about conclusion and also and the rest of the program. So every x86 program needs to have a main function. Okay, the operating system is going to jump into your program and it's expecting to jump to the label main. Okay, so you need to have this main label here with this directive globl for global space main that says that this is a label that's visible from outside the program. Okay, the operating system needs to see this label to jump in. Okay, so then what we're going to put at the start of this main is this prelude. Okay, so this first part here is the prelude. And this is some bookkeeping that has to happen to set up the frame that we talked about before. Okay, so the first thing we need to do, actually, let's go back and look at that frame. You'll notice the first thing here is like, okay, this return address is supposed to be at the top of the, you know, at the front of the frame. Well, that's actually already handled. When the operating system does a call queue, that's going to go ahead and push the return address onto the stack. So that's already happened. We don't have to deal with it. Oops. But we have to deal with the second thing, which is we need to put the old base pointer onto the stack. Okay. And so what we'll do here is we need to do a push queue of the RBP. Okay, so the push queue instruction uses the stack pointer, the RSP, to know where to do the write. Okay, so it's going to write the RBP, the argument here. It's going to write the contents of that register into wherever the next slot after the stack pointer, and then the push queue instruction moves the stack pointer down by 8 bytes. Okay. After that, we also need to move this. We need to, you know, we want to move our stack pointer. Actually, no. Let's go back to the frame here. In my notes here, I've also, oh, right, we need to move the base pointer. Right, the base pointer, right, you know, it used to be whatever the base is of our caller, okay, in the operating system, okay, but we want the base pointer to point to this second slot, okay, which happens to be where the RSP currently is. So the next thing we're going to do is we're going to say, okay, let's move. We're gonna change the base pointer by copying the current RSP into the RBP. Okay. So now the base pointer is where we want it. It's pointing to that second slot in the frame. Okay. Then now the next thing we need to do is we need to move the stack pointer past all our local variables. Okay. We have 2 local variables. Each one takes 8 bytes, right? 2 vars times 8 bytes means we need to reserve 16 bytes. So what we're going to do is we're going to move the the RSP down by 16 bytes by doing a sub queue. Okay. And at that point, after we've done that sub queue, our frame looks the way it's supposed to look. Okay. We've got, you know, our base pointer, the old base pointer has been saved. Our new base pointer is where it's supposed to be. Our stack pointer is where it's supposed to be. Okay. And so at this point, we can go ahead and jump to the start and start executing, you know, all these lovely instructions. Okay. Okay, now the last part is the conclusion. I want to put that over here. Conclusion. Okay, now the conclusion, right, we're going to jump to it after we're essentially done with the program. And our conclusion needs to sort of clean up after ourselves. Okay, so we've made a big mess on the stack. We need to clean up and we need to jump back to the operating system. Okay, so we kind of need to undo everything we did in the prelude. Okay, and it's sort of good to think about this as if we're like going back in time, sort of undoing everything in the reverse order that we did it to begin with. Okay. So the last thing we did is we subtracted 16 from the stack pointer. Did I say snack pointer or stack pointer? I might have said snack pointer. I think I'm getting hungry.
Yeah, you said snack.
I'm getting hungry. I think I need to go eat a granola bar or something. All right. Okay, so we're going to add 16 to the RSP. Okay, so we're undoing that subtract 16. Okay. Now the next thing that we did was the previous thing that we did was the move queue of the base pointer. Actually, we don't have to worry about the base pointer. We don't care about our current base pointer. What we care about is the old base pointer. Okay, so we're going to do a pop queue. And that's going to put the old base pointer, which was on the stack, right? We put with this push queue here, we put the old base pointer on the stack. Now we need to take it off the stack, put it back into RBP. And so that's what the pop queue does. Okay. And then the very final thing we do is the ret queue. Okay, now ret queue does at least two things, if I remember correctly. The super important thing is that it's going to jump, well, it's going to look at the return address, which is where the stack pointer is currently pointing. So it's going to look at the stack pointer and be like, okay, give me that address and jump to that instruction. Okay, so that's one thing that it does. The other thing it's going to do is it's going to move the stack pointer down by 8 bytes. Okay, essentially popping that return address off the stack. Okay, so now the entire frame is no longer, you know, is now, you know, below the stack pointer. So that can be, all that memory can be reused by whatever the operating system wants to do next after having called our program. Okay. And that is it. Question from Jenner.
I think it is important to note here where does that 16 comes from. I think you missed that at the end of assign homes. We before the assign homes we had that locals information, and after the assign homes we produce another information which says stack size. That is
right, because it's the most convenient place to figure out the stack size is in the assign homes pass. Okay, and so like what Jenner is saying is what you want to do is to add to this info field, you want to add a stack size thing that says, hey, okay, we had 2 variables. we need the stack size to be 2 times 8 is 16. And you can stash that in the information of the program AST node. You'll ignore it as you're doing patching instructions. But then when you get to this print x86, then you'll just be able to, when you need to lay down this number here, you'll just be able to look up the stack size that you've already computed. And that's coming out of the info field. Stack size is gonna go into there.
On a related note, the that info field, there is no specification in the grammar for that info field, so you can keep it however you want. Like with Franklin, we did in the office hours, we just const the symbol LOCALS with
the list of variables.
Right.
Yeah. And in general, what I suggest doing with the info, the way I handle it is that I make it be an association list. Right. So it's gonna, like, let's say you have, like the symbol locals, and then const onto, your actual X, Y, Z, or whatever. And then, but let's say maybe you have, that's still there, and you've got maybe stack size. So stack size is a symbol, and that's const with, 16. And you could have, maybe once we have more passes, you might have more kinds of information in here. And the idea is that you'll use the key in your association list to say, okay, what kind of information is this? And you can just do a lookup for that key to find what information you want. And you can sort of ignore the rest of the information in there, and then use that key and then pull out the value that you want. Yeah, so that's a good point. Got a few minutes left in class, so definitely if you have any questions, feel free to go ahead, even if it's a little involved. Go ahead and ask now. And again, I should say that it seems like Slack's been working out pretty well for questions. I can't guarantee to be on there 24/7, but definitely it doesn't hurt to post your question there. And quite often during the day, I'll see it and be like, okay, great, I can answer that. Or Janitor's on there as well, and he's been answering questions. And so quite often you can get some quick turnaround on a question.
Also, for the GitHub repositories from group D and E during the lecture, I got their URLs for the GitHub accounts, and it would be nice, group A, group B, group C, it would be nice if you can just send me your repository, because that is the repository that I'm going to be pulling from.
Mm-hmm. And also, the sooner you get those repos up and give us access, the sooner, if you've got questions, your question could even be like, hey, could you take a quick look at this? Are we on the right track? We're happy to, be like, yeah, oh yeah, you're doing great, or oh, maybe think about this, maybe think about an example program and what might happen as, for a particular pass. So the sooner you can do that, the sooner we can help you out. All right, maybe one more minute for questions. And also, I'll be available for office hours after lecture here. So I'll just take a quick break and then I'll be back online in that other Zoom meeting room.
I don't exactly remember, but in one of the previous lectures, you mentioned that one of these passes is O of n squared or something like that. I can't really feel which one of it now.
Yeah, so right now, none of them
Okay,
are,
cool. Yeah, got it.
it's because this assign homes pass. So this assign homes pass that I've just described is O of n, okay?
Yeah, yep.
But when we make it fancy next week,
Okay.
or the week after next, when we make it fancy and do a really good job of using registers, then it's going to become n squared.
Okay, got it. Yeah.
Yep. So good question. Yeah, and once it becomes n squared, it's going to dominate the whole rest of the compiler. And I mean, one thing I should say, like with this print x86 pass and all these, the prelude and the conclusion, you have to get it exactly right. X86 is completely unforgiving, and it doesn't do anything for you automatically. There's really no magic whatsoever. It just does exactly what you say. If you leave something out, everything just goes badly wrong in weird ways. It's not like you get some nice exception immediately saying, hey, something's wrong. No, it'll just start writing, you'll get goofy values in registers or memory, and wrong things will start happening. And so I encourage you to drink a lot of coffee and maybe, write some of the, definitely get enough sleep if you can, and if that's possible, and try to write the code when you're clear-headed, and then have your teammates read over your code, and maybe even, it might be worth explaining your code to your teammates. Do a code walkthrough and be like, okay, this is why I'm doing this part, and this is why I'm doing that. And that sometimes you can, as you're trying to explain it, you'll be like, oh, wait a minute, I've made a mistake here. And that, and also do read, I definitely encourage you to read the textbook. I know it's not cool these days to read books anymore, but it's got a lot of good stuff in there, and you can sort of read it at your own pace. And there's things that I've gone through fairly fast in lecture that you'll see. You've got examples to work through and things like that in the book. So encourage you to take a look. Alrighty. Well, with that, I think we're out of time. And so I'll see you in office hours or next week in class.
See you later.
Ciao. All right.